going to C? A going to C is 1. Is A going to D?
No.
Right? A to D is what? 0 or 1?
0.
0. So A to D is 0. Going to B here. B, is it going to A?
No.
B going to B? B going to C? B is only going to whom? D. Yeah, put 1. Alright? Okay? That's the difference between a direct and indirect. The last one is which one? You notice, what about C? See, does C go to any other vertex?
No.
Right? Okay? So C is not going to any other vertex. That's why all of them 0. Alright? So if we start from C and I ask you, go, travel, go somewhere, you stuck or not? You're stuck, correct? Alright? So, be very careful with this one. Next we have adjacent list. Okay? What is the adjacent list? Okay? It is, I have the set of vertices and the set of edges. I have something called the head, which is my starting point, just like a linked list, right? I have the head, right? And I have the list. Now looking at A. A is adjacent to which vertices? Mean, A is directly connected to which other vertices? Which one?
C.
Is directly connected to B, C, and D, right? There's connection to all. So here, A is connected to B, C, and D. What about B connected to which one directly?
A and D.
A and D. What about D?
Only A,
What
B.
about C? Only A, right? This is called adjacent list. Right? It seems many like this is the first time you study it. Alright, adjacent list for what? This is directed graph, correct? Okay. A is adjacent to which vertices? B, C. B is connected with vertices adjacent? D. C? None. D? A. Right? This is important. Why? So for example, you started from vertex A. I said to you, travel. Probably, if you want to travel, you want to find the shortest distance between which one? A to B is shorter, A to C is shorter, or A to D is shorter, correct? What we do with shorter? To choose the shortest path, correct? So to not choose the longest path, right? This is every day you do it, correct? When you wake up from home, coming to your lecture here, right? In your brain, you are doing the shortest path. You will go maybe through B1, then you go to the garden, then go to A5, then A4. You will not go to A1, correct? Then you come to A4, right? You will not maybe go from there, I don't know, maybe shorter. Who knows? You know better, okay? Especially based on your location, right? Right? So every day actually we are doing these things in our brains. Alright? So this is undirected graph. Undirected graph consists of set of vertices, set of edges. Why I put here? Because sometimes you see it in the book, how they represent it in the mathematical form, right? Look at the V. What the V here represents? What this V represent?
Vertices.
Set of vertices. That's how we write it, V uppercase letter, right? Set of vertices. Graph here, right? Then I put the set my vertices. What's E here represent? Set of edges, right? For the graph one, which is this one called graph one. What is the graph one? Sorry. Something deleted there. Anyway, this set of vertices, set of edges, I think we should be fine. Okay? Directed against versus undirected graph, right? This is only about terminology. We know what is directed and undirected. Now, what about 5 and 7? Right? Okay, sorry. So here I have this graph, right? Not yet. I'll explain that later. I have this graph, right? So the set of vertices for this graph will be these vertices, correct? Okay? And the set of edges for this graph will be these set of edges, right? Okay? By the way, if I have undirected graph, you should not put 1 to 3, then 3 to 1, undirected. Only for directed you do this, correct? Only for directed now, I have vertex 1 to 3, then I have 3 to 1, correct? But if it is without arrow, no need to repeat them. It's unnecessary, okay? All right. Okay, this is a tree or graph? Tree and graph. Tree. Both, right? Can be both tree and graph. All right. This is a set of vertices, set of edges. It should be fine. Okay, yeah, this one. So, adjacent nodes, right? You can see 5 and 7, right? Okay. Now this is, if it is undirected, correct? 5 going to 7 and 7 go to 5, right? Then they are adjacent to each other, correct? But now, 5 is going to 7, but 7 is not going to 5. Why? Because it is a directed graph, right? Since it's directed, what we can say, 5 is adjacent to 7. Or 7 is adjacent where? From 5. Okay? That's the terminology. So we know that is the arrow going from which vertex to which vertex. Alright? Okay or not? Good tired. Right. Alright, we will read something interesting. Right? Maybe boring for some. Okay. Now, I have this graph. How many vertices I have?
A lot.
4. Now you need to do calculation, right with me? Okay. What is the number of edges in complete directed graph? Meaning that every vertex connected to all other vertices. What is the total number of edges?
1, 2, 3.
How did you come up with 16?
12.
Use the equation here, right? Okay. It's good to know, right? Okay. Sometimes the graph will contain hundreds of vertices, correct?
Yeah.
Then how we calculate? You will count them one by one. Does it make sense, right? So the total number of vertices is what? Very short.
N into N minus 1.
Who said 12? Who said 12?
16.
Yeah. Correct, 12, correct.
Yeah, 12.
This is what? Bigger of N.
N.
This is the complexity.
Yeah.
This is what?
Formula.
This is the equation to calculate the total number of edges. What is the N value here?
4.
4 multiplied by 3 equal to what?
12.
12. That is the total number of edges.
12.
Okay?
16.
Now, this is directed or undirected?
Undirected.
Undirected. How to count? So, if I have a complete graph, will I have same, less, or more edges compared to directed?
In directed you have more. 2 times more.
Directed need to have more. Why? Because if I want to connect A and B, let's say in the previous graph, A and B to A, I need 2 edges, correct? But here to connect 2 vertices, I need 1 edge. So, what is the total number of edges in complete undirected graph?
N into N.
I want to trick you. What's the total?
6.
Good. Okay. Equation here. What's the number of vertices? 5. 5 multiplied by what?
4.
4.
20.
20. Divide by
10,
2.
10, 10.
Yeah, this is the total number of edges.
What do you call
Okay or not? Alright. Next we have this graph, right? This one. So the graph we represented first, it was A, B, C, D, correct? The first row for A, second row for B, third row for C, and so on. Why are we doing this? Because A comes first alphabetical order, right? A, B, C, D, and so on. We keep continuing. But now, is it possible to have vertices not A, B, C, D? Yes.
Dallas,
Which vertices I have now? States or cities or locations, right? I can have anything, right? So now looking at this graph, I have states, okay?
Denver.
United States and states of America, right? I have Austin, for example. First, is this directed or undirected?
Directed.
Directed. So Austin going to Dallas, what is the distance?
200.
200 meters.
200. Dallas going to Austin, same, 200. Let's say here, Denver to Atlanta, how much?
1400.
1,400.
Can I go from Atlanta to Denver? No, right? Because it is directed, right? Okay. So I have all this. Now, how can I represent this graph? Adjacent matrix, right? How can I do the matrix? For A, B, C, D, first row A, second row B, second row C. Here, how can I do it?
Not name of state.
Yeah, how can I represent it? Is one two-dimensional matrix enough?
Yes.
We do the two-dimensional matrix enough for us for A, B, C because assume first row is A, second row is B. So it's very easy for me to link. So if row 0, right away I write A. If row 1, right away I do B. But here if row 0, which one? So I need to label them, correct? I need to know which one you should put it as city 0. which one will be city 1, which one city 2, right? So what I need to do, I need to design one-dimensional matrix. If I put Atlanta at index 0, I mean the first row will be for Atlanta. If I put, which is, okay, so there are two ways to implement it, array-based implementation and linked list-based implementation, okay? Right? And the array-based implementation, I will do one-dimensional array used to represent what? The cities, the vertices. And I have two-dimensional matrix to represent what? The connection between these two cities, or every two cities, right? Okay, and it will look like this, okay? The graph is there, easy, step by step. This is the graph, correct? Okay, this is the graph, so we can right away relate. The first one here is a one-dimensional matrix, right? One-dimensional array, sorry, one-dimensional array, right? So which one has index 0? Which city?
Atlanta.
So which state? Which one? Atlanta, right? Then at the next one, what? Austin. So we assume first row, or row 0 is for which city? Which state?
Atlanta.
Row 1?
Atlanta.
For Austin. Row 2? Chicago, and so on. And we keep continuing. Now it's easy for me to find the connection, correct? So let's go to the graph and find me any connection. Let's say Houston and Atlanta, right? Houston to Atlanta 800, Atlanta to Houston 800, correct? Let's go. Atlanta is where? I want to do Atlanta to Houston. Atlanta is where? So I do search algorithm, right? Where's Atlanta? I found it. What is the index? 0. Where is Houston? I need to find it. Where is Houston? 5. So I go to the matrix, 0, 5, array of 0, 5 equal to what? 800. Equal to 800. Array 0, 5 equal 800. Simple? Very simple. Okay? So actually, it is I and J, correct? I is the row, J is the column. So I'll have to tell you, array of I and J equal to 800, for example. Array of 0, 5 equal to 800, and so on. So it's very easy to input. So I will give you the I will give you the J, and I will give you the value. You just need to input. Correct? Okay? So this is what is given to us. It's given to us, and you just need to input. Now, Houston to Atlanta. Houston is where? 5. Atlanta is what? 0. So 5, 0 should equal to what? 800. And so on. Another example. Let's do it there. Okay? I have Washington to Dallas, right? Okay? Washington. Where's Washington? 6. What is Dallas? 3. So 6 and 3 should equal to what? 1,300. So I'll go to 6, 0, 1, 2, 3, 1,300. All right? Do I have Dallas to Washington? Do I have connection between Dallas and Washington?
Yes.
No. What I put? 0. That's it. Simple? Okay. Next, I have linked list implementation. Right. By the way, it's not all in the, it can't be all the time in this. All right? But I can have one-dimensional array to represent the vertices, same like the previous one, right? Same like this one exactly. One-dimensional array to represent the cities, but the connection between two cities, I put it in a linked list. And see, this is how. So then a list is used for each vertex V, which contain the vertices which are adjacent from V, right? And it will look like this. So same graph. I have same graph. I have same the one-dimensional matrix, but actually every location inside the one-dimensional matrix is what? What exists there? Array of 0 is what? What is inside?
Atlanta.
I know it's Atlanta, but what is it?
The head.
Head, correct. Every location is a head. Why?
Go to another list.
Exactly, because every array of 0 is a linked list, correct? Array of 1 is another linked list. Array of 2 is another linked list. How can I create this in programming? How can I do this? Can I declare array of objects?
Yeah.
Let's say. Can I declare array of objects? I have class 1, right? How can I declare array of object of class 1? What should I do? If I write int array of 5, I declare array size of 5, all these 5 elements are what?
Integer.
Integers. If I change n to what?
1.
To 1, I'm declaring what?
Array of 1 plus 1.
Mean array size of 5, every location is an object. So array of 0 is an object, right? Array of 0 is an object. To access the element, I write array of 0 dot. Then I do the functions and so on. Correct? Okay. Now, I don't want what? I want pointers inside, correct? Okay. So I can actually assign head inside every location. Array of 0, assign head. Array of 1 is equal to head, and so on and so on and so on. Right?
So that become 1 star or just 1?
Sorry?
The declaration.
Declaration becomes what?
1 star or just 1?
1 star or 2 stars, you're asking me?
No. Should we put a
Until
star
they're
or not?
having a test.
Leave it for now, okay?
Until
Let's
they're
look at
having
it.
a test.
We'll put star. So this is mean array of everyone is what?
Not money.
Okay.
Is an object, right? Okay. To do this one, we need to write equal and new. Okay? Then that's why I leave it. Okay? Don't worry too much about the programming now. Imagine just every location is what? Is a head. I can simply write array of 0 equal to head 1. Array of 1 equal to head 2. Equal to what? Equal to head 1 is what? Atlanta. Okay, head 2 is what? Austin, and so on, right? Okay, so I can create a pointer, Austin, a pointer for everyone, correct? And I can assign it as array of 0, array of 1, array of 2, array of 3. Just make it as simple as this. Don't worry about the implementation now. Okay, so I can declare a pointer, right? I can declare a pointer, let's say Atlanta, right? Atlanta, correct? This is a pointer, type in class 1, and I put this one in array of 0. Okay? Array of 0 equal to Atlanta, this is done. Okay? So now let's continue. The idea here, Atlanta, if I go to Atlanta, where's Atlanta? Here. Atlanta, the first one is connected to which one? Let's say connected to 6. Which one 6? Washington, right? Atlanta to Washington is what? 600, correct? So now I want to insert Washington to my linked list, correct? So I come to here, I need to find. Where's Atlanta? Okay. What is the adjacent list for Atlanta? Is Washington and what? Washington and Houston. Houston and Washington, right? Let's do Washington first. So what I did, simply, Atlanta next equal to what? Equal to what?
6.
Equal to 6. 6 is which one? Washington, correct? What is the distance? 600.
600.
I can add one more field for what? For the name as well. No problem. But if I know the location, can I know the name?
Yeah.
Yes. So it's okay. The location is good enough for me. Okay? So every node has what? Index of the adjacent vertex, weight, and appointment to next. Mean is connected to whom, and what is their distance. Correct? But why I did this one first, Atlanta? Because now I want to insert another node, correct? Which is which one? Houston. Houston at which location? 5. I should insert Houston at the beginning or at the end of the linked list? Beginning. Why not at the end? More complex, okay? Less complexity to insert it at the beginning, right? So when I have now Houston, Houston at which index? 5. So I insert 5 with the distance what? 800. Before what? Before Washington. Okay, that's the idea. Okay, it's fine. You can flip them. It's okay, up to you. No problem. Okay, but the whole idea is what? I insert front. I don't insert at the end. And of course, I will not change the head, right? I insert right away between the head and what? And the first one. Okay? It's not exactly insert beginning. Okay? Insert after the head. And this one is very similar of what? If I have a head, right? That I don't want to store value in it. Imagine like this. If the first node in the linked list is 10, right? And I want to insert 5. So I will not insert it here. I will insert between head and 10, correct? Okay? Because head doesn't have a value. Head is what? Just the starting point of the linked list. So imagine this one also just a starting point, right? Starting. Is this clear now? Okay. So coming to here, Chicago here. Where is Chicago? There. All right. Index 2. Going to where? Going to Denver, right? Denver is what? Denver is 3 to 4. Right? Where Chicago?
4.
3 to 4 is what? 2. Okay. Chicago 2. Yes, yeah. 2 to 4, sorry, 1,000, right? Okay. But is Chicago connected to anyone else? No. So I have two ways of implementation, right? Which one do you think better? I have the array-based implementation, or the matrix-based implementation, or linked-list-based implementation. Which one is better?
Array.
Why array better?
Easy.
Do we care about programming effort?
Complexity.
Don't say yes, say no. We care about complexity. Programming effort doesn't matter, right? Once I did my linked list structure, do I care about linked list complexity? We have now the code for linked list. Now if I implement something with linked list, do I care about complexity anymore? No. Insert node, insert 10, insert 20, insert 30, delete. I have everything like a function, correct? It will be as easy as array. Nothing will change anymore, right? We already implemented, right? Now if I have everything implementation all set, which one is better in terms of complexity, right? Which one do you think?
Linked list.
Linked list. I say matrix. Who agree with me, matrix? I say linked list. You know why? There's a reason why I say it this way. It depends on the situation. Okay? That's why we learn both. If one better than the other in all scenarios, then I need to learn only one, correct? Why in binary we didn't learn how to implement an array, in tree, sorry, only in array? Because I don't need a tree. But here, we need both, because in different situations, different scenarios, I will need different representations, okay? And here comes where? Adjacent matrix versus adjacent list representation. So what I have, first, adjacent matrix, the two-dimensional matrix, okay? So, good for density graph. What is density graph?
Some of the edges are
Only
missing.
few are missing, right? I have a lot of connections, right? Meaning I have a lot of edges. Okay with me? If I have a lot of edges, what will happen to my two-dimensional matrix? Mainly full, right, with elements. I will not have many zeros inside, right?
Yes.
Okay. Why is good? Because I can access the index right away very easily, correct? Okay or not? Okay. Compared for adjacent list, good for what? Good for a sparse graph. So the linked list is good for what? What is a sparse graph? Only few connections. If I have many connections, what will happen to the list? List become very long, correct? To find the connection between Dallas and which one for Denver? To find the connection between Dallas and Denver, I come to Dallas. Is this Denver? No, go next. Is this Denver? No, go next. If my list here is very long, correct? And complexity will be every time to find the connection, correct? However, in the matrix what? I can quickly right away find the connection. Right or not? Here to find the connection between Dallas and Denver. Dallas is what? 3. Denver is 4. So 3, column 4, then I can know the connection between them.
It's
Right?
the complexity one?
Complexity 1, exactly.
Yes.
But I need to find the cities. Okay? The cities here, finding them, the complexity is not 1. But in both situations, I need to find the cities, right? In which location?
Yes.
Right or not? Okay?
Yes.
So here the complexity 1 to identify, correct? For density graph. How about for a sparse graph? If this graph is sparse, okay, what is the complexity of finding connection?
Sparse? What does sparse mean?
Sparse mean the only few edges are there. Very few edges there.
Then it's easier than n.
What's the complexity? Don't tell me it's easy. Huh? No. What's the complexity finding the connection?
Log n.
No. N, no.
And log n.
What is it?
Which is more log?
Constant also.
1.
Yes. Because what will happen if I have a sparse? Every vertex, every head is connected to 1. At most is 2. Actually, the majority is 1. So you have 1, 2 operations, 1, 2 operations. At most going to be 2 operations. Right? Because it's sparse. Sparse mean what? Only few edges there. So the edges actually less than the vertices or more than the vertices? Okay? Of course, it will be less or very little.
Yes,
Okay?
maybe.
Will never be more than that number of vertices. Look here. Hey, here. Okay, this is what? Okay. This is what?
This is tree and graph.
This is sparse graph, correct? Sparse graph, right? Okay. Number of edges more or number of vertices more?
Number of vertices more.
Vertices more. So if I want to present the graph, the presentation here using adjacent list, right? So this one will be connected to 1, right? This one will be connected to 1, and this one will be connected to 1, and that's it. And if it's directed, it's even less, right? Okay. So this one is connected to 2, but only happen if it is I have something like this. Okay. In some situations, yes, but this is I mean, almost I've never seen something like this in my life. Okay. One connected to all others, and no one connected to all. It doesn't look sparse anymore, right? Okay. Anyway, so the complexity will be much more less. It will be equal to constant. In the most situations, it will be constant. In very rare scenarios, it will be, okay, 1. So, looking here, good for decigraph. What is here the complexity? So here, what is the E?
Edges. Set of edges. The value of edges.
Okay, E represent what? Edges, right? V represent what? Why vertices squared?
Edges.
Yeah, 2 loops. Right, 2 loops. 2-dimensional matrix, I need what? 2 loops, right? I have 2-dimensional matrix, correct? Okay, so good for decigraph. The complexity will be V to the power 2. Vertices matters more, right? Okay. Memory requirement. What about memory requirement? I need what? 2-dimensional matrix. So the same thing. So based on the vertices here. So how many rows, how many columns is based on vertices. Okay. So connectivity between 2 vertices can be tested very quickly, correct?
Yes.
So adjacent list, good for sparse graph. Why V? Why not V squared?
Only one.
Because you notice that I have the number of vertices is very similar to the number of edges, correct? They are almost equal, so actually it doesn't matter if it's V or E here, doesn't matter. They are relatively the same,
Yes.
correct? They are relatively the same.
Sparse graph.
Sparse graph all the time, edges and vertices, they are very close to each other. Okay? So that's why they are the same. Okay? Memory requirement is what? Also the same. Okay? I need only V number of nodes, correct? And that's it. Okay? Then vertices adjacent to another vertex can be found very quickly. Since I have 1, maybe 2 connections at most, can be found very quickly. Correct? Okay, take a break. Take a break and we start with